Hello students, welcome to my channel. This is learning. This is a MCQ solving episode. Today we are going to solve some problems on aliphatic hydrocarbons, that is alkanes, alkenes and alkynes. So let's start. The first problem is this compound is given. When this compound is treated by hydrogen in presence of Lindlar's catalyst, what will be the major product? We have to identify the major product A. First of all, I have written the answer. This is the product contains the cis double bond. We know when triple bond is reduced, partially reduced by Lindlar's catalyst, the two hydrogen atoms are supplied from the same site of the triple bond. So this is a syn addition process. We know palladium hydrogen gas is adsorbed on palladium surface, and this palladium surface in Lindlar's catalyst, this palladium surface is poisoned by lead acetate or maybe quinoline, maybe sulfur. So these two hydrogen atoms are supplied from the same site of the triple bond. So this is a syn addition process, and as a result of that we get a cis double bond over there. The two hydrogen atoms are supplied from the same site, so we have the cis double bond. So definitely we have to remind always that the catalytic hydrogenation process is a syn addition. The syn addition process. So our product is the cis double bonded compound. So here option 3 is our correct answer. Okay, next. Now move to the next problem. Now in this problem the 3-methyl cyclopentene molecule is given, and this molecule is treated by bromine, one equivalent of bromine, in presence of photoenergy or heat. Now our question is, which will be the least probable product among the given four? Now if one H dot, that is hydrogen free radical, is removed from here, removed from carbon number 3, this free radical is obtained, and one free radical, one H dot, is removed from carbon number 4, the free radical 2 is obtained. If one H dot is removed from carbon number 5, free radical 3 is obtained. If one free radical one H dot is removed from the methyl group present outside the ring, the free radical 4 is obtained. If one H dot is removed from 1 and 2, 5 and 6 free radicals are formed respectively. Now the question is, in free radical 1, free radical 1 is a very stable one, right? Because in free radical 1, this is a 3-degree free radical, and of course the free radical is formed as a allylic position. So there is resonance involving the double bond here, and the hyperconjugation of course there, because there are 3 and 2, 5 alpha hydrogens are there, and of course the plus I effect of the alkyl groups are there. So free radical 1 is a very stable one. Now in case of free radical 2, this is a 2-degree free radical. This is less stable than free radical 1 and 3 of course. In free radical 3, look at here, this is again an allylic free radical, right? And of course it is 2-degree. So resonance over there, and resonance involving the double bond over there, and the hyperconjugation involving the 2 alpha hydrogens at the carbon number 4 is present there. Look at here, in free radical 4, this is a 1-degree free radical and no resonance is involved there. So the free radical 4 is relatively least stable among the 4 free radicals. And look at here, in free radicals 5 and 6, these free radicals are very unstable because these are vinylic free radicals. The two carbon atoms are double bonded. So 5 and 6 free radical formation is virtually impossible, right? So when bromine dot is attached to free radical 1, the monobrominated product 1 is obtained, and when Br dot are attached to the respective free radicals, the respective monohalogenated product are obtained. So the determining factor is that the stability of the free radicals. Definitely free radical 1 is the most stable one. Free radical 3 is then most stable, and then free radical 2, and then free radical 4. So and of course we know in bromination reaction the order of reactivity of 3 degree, 2 degree and 1 degree hydrogen is around 1600:82:1. So in bromination reaction 3 degree free radicals are reacts in a very large margin, because bromination is more selective process than chlorination. The order of the amount of products in this reaction is definitely 1 is greater than 3, greater than 2 and greater than 4. Hence the least stable, the least probable product is of course compound 4. So our answer is option 4 definitely. Okay. Problem is the order of decreasing reactivity of the alkenes towards HBr addition. Now in the first example, look at here, the HBr addition is actually as an electrophilic addition process. In the first step, the double bond attacks the H plus ion over there, and Br minus actually leaves the substrate, leaves out. So this carbocation is formed, and look at here in compound 1, this carbocation is stabilized by the plus R effect of the adjacent CH3O group. So this is a very stable carbocation, and Br minus then attacks at the carbocation to form the product. So in the electrophilic addition process, the first step actually is the rate limiting step or rate determining step. So as stable the carbocation is, the rate of reaction is higher. So in compound 1, the carbocation is very stable definitely. Look at here in compound 2, definitely carbocation is formed, and nitrogen is involving in resonance there. The plus R effect of nitrogen operates there. So this resonating structure is possible, and definitely the stability of this resonating structure is definitely higher than the carbocation obtained from compound 1, because this is here it is NH group, NaCH3 group, and in compound 1 this is OCH3 group. We know the electron donating ability of NHCH3 is greater than OCH3, obviously, because nitrogen is less electronegative than oxygen, so its electron donating capability is greater than that of oxygen. So the carbocation formed from compound 2 is more stable than that obtained from compound 1, and then Br minus attacks the carbocation and the product is obtained. Now in case of compound 3, the double bond donates its electron to hydrogen, and this carbocation is formed. Now in this carbocation, nitrogen of course there, but it is not at the adjacent position with respect to the carbocation. So the plus R effect of nitrogen doesn't operate here, only the minus I effect operates here. So this minus I effect of nitrogen definitely destabilizes the carbocation. and then Br minus attacks the carbocation to form the product, right? So the stability of the carbocation obtained from 3 is much less than that obtained from compound 1 and 2. And in case of compound 4, the double bond attacks the H plus ion, Br minus leaves the substrate. So the carbocation obtained is formed from compound 4 is stabilized by the plus I effect and of course the plus hyperconjugation effect of the methyl groups. We know the plus R effect is stronger than hyperconjugation effect. So definitely the stability order of the carbocation is definitely the carbocation obtained from compound 1, then compound 4, and lastly the carbocation from compound 3. So the reactivity order definitely would be 2 greater than 1 greater than 4 greater than 3. So the order of reactivity of the 4 compounds is in the order 2 greater than 1 greater than 4 greater than 3. That is option 1 is our correct answer. Okay. Next moves to the next problem. The next problem is cyclohexene molecule. If cyclohexene molecule is treated by cold KMnO4, cold alkaline KMnO4, and in another reaction it is treated by paracid followed by acidic hydrolysis, the different products are obtained. And now question is, what are the products A and B? What are the products A and B? Now look at here, when cyclohexene molecule is treated by cold KMnO4, this manganate ester is obtained, and of course we know this is a syn addition process because the negative charge of the negative oxygen of MnO4 minus attacks from the same site as the double bond attacks the oxygen, double bonded oxygen attached to manganese. So the two oxygen attached to the double bond from the same site. So this is a syn addition process, and followed by alkaline hydrolysis we get the product, the cis isomer. This is cis 1,2-diol, cis cyclohexane 1,2-diol. And if we treat this molecule, this cyclohexene molecule, by paracid, this epoxide is formed, and we can find the we can write the epoxide formation process in this way. So the oxygen, the peroxy oxygen attached to the double bond from either side of the double bond, and this epoxide or oxygen is formed. Now in the second step, when hydrolysis is carried out, the protonation of oxygen occurs, and after the protonation of the oxygen, the water molecule attacks from the opposite side of the bridged oxygen atom of the epoxide. That is, the two oxygen atoms are attached from two opposite sides. So actually we get the trans isomer, the trans product. So this is actually a trans addition process and anti-addition process. KMnO4 addition is a syn addition process, and paracid followed by hydrolysis is a trans addition process. As a result of that, we get two different isomers. In KMnO4 addition we have the cis isomer, and in paracid addition and followed by hydrolysis we get the trans isomer. So we can write the two isomers in this way. We can write the isomers in this way, that the cis isomer is actually a equatorial axial isomer. This is EA isomer, it is written as EA isomer, and the trans isomer is actually equatorial, that is EE isomer. So the two isomers of cyclohexane 1,2-diol. So in K-4 addition process we get the cis isomer, and in para-acid addition we get the trans isomer. So option 2 is our correct answer. Here A produce the cis isomer and B produce the trans isomer. Now we can show the two isomers in this way. Look at here, this is our compound. Look at here, this is our molecule, that is equatorial axial isomer. Look at here, this is a cyclohexane chair, and this is our equatorial bond, this is our equatorial bond, and this is our axial bond. So this is actually equatorial axial isomer. This one looks like this. This bond is equatorial, this bond is axial. This is a cis isomer. So these two oxygen atoms comes from the same site by K-4 addition. So this is our cis isomer, and this is our trans isomer. Look at here, this is our trans isomer. The two OH groups are like this. This is our cyclohexane chair. Look at here, this OH bond is like this. This is this OH bond, and this is our OH group attached to this carbon over there. So this is our equatorial OH group, this is our equatorial bond, and of course this is our equatorial bond. This bond is present below the plane and this bond is present above the plane. So these two are, this one are actually is actually trans isomer, that is the two OH groups are present. This one is the above the plane bond, that is the upward bond, and this one is the downward bond. So this one is actually equatorial isomer, and this one of course is the axial isomer, axial equatorial isomers. Two OH groups at the same side of the plane. So this is our cis isomer and this is our trans isomer. Look at here, this is our trans isomer. Here in the left compound, two OH groups are attached, two OH groups are present in the downward bond, and in right compound the two OH groups are in the opposite directed bonds. One is upward and one is downward. So the left one is the cis isomer, the right one is the trans isomer. Okay, moves to the next problem. In the next problem, question is, in which compound do not produce carbon dioxide, which compound doesn't produce will not produce carbon dioxide on oxidative ozonolysis. Now question is oxidative ozonolysis. In the first compound, this is an alkyne and terminal alkyne definitely. When this terminal alkyne is treated by ozone gas, these two 1,2-diol are obtained by cleaving the two pi bonds over there. Then oxidative ozonolysis means no zinc dust is added, so hydrogen peroxide is produced, which will oxidize the two carbon atoms, carbon containing the oxygen atoms. Here this is a oxidative cleavage. This carbon-carbon bond is breakdown, and two OH groups are attached. So in the left portion we have the acetic acid molecule, and from the right portion we have the formic acid molecule, right? So in the formic acid molecule there is a carbon hydrogen bond, which is a weak bond. Hydrogen peroxide will also oxidize, will also cleave that carbon hydrogen bond to produce another carbon oxygen bond, and this carbon oxygen bond, this is actually a geminal diol. Two OH groups are attached to the same carbon, and after removal of water from here, after removal of water molecule from here, we get the carbon dioxide molecule. In compound 2, this is a styrene molecule, PHCH double bond CH2 molecule. On ozonolysis, it will produce one is benzaldehyde. The left portion gives benzaldehyde molecule, and the right portion gives you the formaldehyde molecule. Now the benzaldehyde is oxidized in presence of hydrogen peroxide, of course, to produce benzoic acid, and the formaldehyde molecule is oxidized to formic acid. And of course this formic acid is oxidized in the similar way as above. It will produce the carbon dioxide molecule, right? So carbon dioxide is obtained from compound 1, compound 2 definitely, and we have from compound 3. In compound 3, when ozone gas is added, this pi bond is cleaved, and cyclohexanone and formaldehyde molecule is produced, and the formaldehyde molecule will then oxidize to formic acid, and then it will produce carbon dioxide in the similar way as above. In compound 4, there is a cyclohexene molecule, methyl substituted cyclohexene. On ozonolysis, this carbon-carbon double bond will be cleaved, and two carbon oxygen bonds are produced, and this the carbon oxygen bond at the right is then oxidized. The carbon hydrogen bond over there is oxidized to OH group, so COH group is produced at the right hand side. So actually the molecule we have is 1 2 3 4 5 6 7, that is 6 oxo heptanoic acid, but no carbon dioxide is produced from here. So actually the carbon dioxide molecule are produced from oxidative ozonolysis, where the double bond or triple bond are at the terminal positions. Look at here, we can verify from compound 1. This is a terminal alkyne, compound 2 is a terminal alkene, compound 3 is definitely a terminal alkene. So these are produced carbon dioxide from the terminal by oxidizing the terminal carbon. But in compound 4, this is not a terminal alkene, so it will not produce carbon dioxide. So the carbon dioxide is not produced from compound 4. So 4 is our right answer, right? This is all about the 5 MCQ we are attempting to solve. So this is all about from the video today. Thanks for watching the video.